Welcome to AI Paper Podcasts, your shortcut to the bleeding edge of AI research. Today, we're diving into a really interesting paper that tackles one of the big frustrations with large language models, their surprising lack of memory. We're talking about Dynamic Cheatsheet, test-time learning with adaptive memory. The authors are Marek Sezgan, Motyuk Sekunu, Federico Bianchi, Dan Jurafsky, and James Zhu. So you know how LLMs can be brilliant, right? They code, they reason, they create amazing text. But every single time you talk to it, it's like starting fresh. No memory of what worked before, what failed, none of those insights they just generated. It's super inefficient. This paper introduces Dynamic Cheatsheet, or DC. It's a lightweight, kind of ingenious framework. It gives these black box LLMs a memory, one that persists and evolves right when they're doing the work at inference time. And the magic is it lets the model store and reuse strategies, useful code snippets, problem-solving tricks, all without needing explicit ground truth labels or human feedback. And crucially, without actually changing the model's core parameters.
Yeah, and the results they got are pretty startling. I mean, get this, Claude 3.5 Sonnet's accuracy more than doubled on the AIME math exams. It jumped from about 23% to 50% on AIME 2024. And on AIME 2025, it went from a really low 6.7% all the way up to 36.7%.
Yeah.
Just by learning to hold on to some algebraic insights using this DC method.
And GPT-4 on the Game of 24 puzzle, that one's even more dramatic. It went from, what, like 10% success?
Something like that, yeah, very low.
To 99% accuracy, basically perfect. And that happened after it figured out it could use a simple Python script to solve it and then just remember to keep using it.
Exactly. It found a good tool and stuck with it.
So this isn't just a small tweak. It feels like a fundamental shift in how LLMs could learn and adapt over time. So for all you AI researchers and ML engineers listening, our mission today is to really unpack this dynamic cheat sheet idea. We'll look at how it works, why it's apparently so effective, and what it might mean for the future of LLM performance and maybe even continuous learning. Let's get into it. Okay, so let's dig a bit deeper into this problem first. This idea that LLMs operate in a vacuum. For those of us working with these models day to day, what does this starting from scratch or de novo approach really mean in practice?
Well, it's such a contrast to how we learn, isn't it? As humans, every experience builds on the last. We learn from mistakes, we remember what worked, our understanding deepens over time. But current LLMs, after their main training is done, they don't really do that. Every new prompt, every query, it's treated like the very first time they've seen anything like it. They end up rederiving the same solutions, making the same kinds of mistakes, because there's no mechanism to hold on to that immediate experience at inference time. It's kind of like having a brilliant student who forgets every single lesson the moment class ends.
Right, so it's not just about lacking general knowledge, it's this very specific lack of task memory, even for things they just figured out minutes ago. How is this dynamic cheat sheet different from other methods people might know, like fine-tuning or maybe standard RAG?
That's a really important distinction. Fine-tuning means actually changing the model's internal weights. That takes a lot of resources, computing power, and usually big labeled data sets. And traditional retrieval augmented generation, or RAG, that usually pulls info from huge static databases. Think of it like giving the LLM access to a giant, unchanging encyclopedia to search really fast. Dynamic cheat sheet is different. It's about creating a memory that's dynamic, that the model curates itself based on its ongoing interactions. It learns and adapts right then and there. We're really talking about online experience-based learning.
I see. So it's not just fetching facts, it's actively generating and refining its own knowledge based on what it's trying to do. That sounds like a big step up. How does the framework actually work then? What are the main parts?
It's actually quite elegant. It's built around two main modules. One for solution generation, figuring out the answer, and one for memory curation, deciding what to remember. And what's really clever is that often the same LLM can do both jobs, just with different instructions or prompts. This makes DC super flexible. You can even use it with models where you can't touch the internals, like the big commercial APIs, GPT-4, Claude, and so on.
Okay, that is pretty neat. Let's look at the first version they talk about, DCQ, which stands for Cumulative. How does that one work when the LLM gets a new problem?
Right. So with DCQ, when a new query comes in, the first thing the LLM does is it checks its external memory. It's asking itself, have I learned anything useful for this kind of problem before? Then it goes ahead and generates a solution, using both its internal knowledge and whatever hints it pulled from its memory. The cumulative part happens after it gives an answer. It then goes into this curation phase where it reflects on the solution it just produced and decides whether to update its memory.
Okay, so it solves, then it reflects and updates its notes, basically. What kind of logic does it use there? How does it know what's worth keeping?
Well, if the solution seemed right, or useful or maybe just a handy trick, it gets sort of codified and added to the memory. But if it thinks it made a mistake, maybe a bad assumption or a faulty heuristic led it astray, it might actually revise that rule in its memory or even delete it. And the really groundbreaking part, I think, is that this all happens without any gradient updates, no retraining the core model, and critically, without needing any external correct answers or ground truth labels. The system is essentially judging its own work.
Wow. Okay. Self-correction without a teacher or changing the model's brain. That's pretty cool. And the memory itself, is it storing like entire chat histories or is it more focused?
Oh, definitely more focused. Highly selective. DC's memory is all about concise, transferable snippets. Think short strategies, outlines of solutions, maybe useful code blocks. Not the whole rambling conversation. And that's really key because it avoids what they call context ballooning. You don't want to flood the LLM's input window with tons of irrelevant stuff. That just makes it less effective and can even make it forget the important parts of the current prompt. Keeping the memory lean and mean is crucial.
Got it. Keep it actionable. So that's DCQ, updating after solving.
Right.
But they also have DCRS, retrieval and synthesis. What was the issue with DCQ that led to this, and how does RS improve on it?
Yeah, DCQ is strong, but it has maybe a couple of spots for refinement. First, because it updates memory after solving, it might miss out on learning something from the current problem that could have actually helped solve that same problem. Bit of a missed opportunity there. And second, it doesn't explicitly store past question-answer pairs unless they become a general strategy, so it can't always look back at very specific similar examples it solved previously.
Okay, so DCRS fixes that by adding a retrieval step before it even starts solving. How does that work?
Exactly. DCRS brings in this retrieval mechanism. Before generating any response, it first looks back into its knowledge base, which now includes past input-output pairs, and finds the top K most similar examples. They use K3 in the paper. It uses embedding similarity, something like OpenAI's text embedding 3 small model, to find these relevant past cases. Then, these retrieved examples, along with the existing memory, get passed to the curator.
Ah, and this time the curator updates the memory before the solution is generated, using those retrieved examples.
That's the key difference. The curator synthesizes insights from the current query and those retrieved examples to update the memory first. Then, the generator module uses this freshly updated memory to produce the final answer. This lets the model leverage relevant history and integrate new insights before it tackles the problem, making it potentially more adaptive and efficient right from the start.
Okay, this is where it gets really compelling for me, the actual results. Let's talk about the performance gains, because some of these numbers are just, wow, the game of 24 seems like a perfect showcase.
It really is. So baseline GPT-4 gets the game of 24 right, only about 10% of the time. Pretty poor, actually. But with DCRS, it jumped to 99% accuracy, an incredible leap. And the reason was pretty clear. The model quickly figured out that writing and running a small Python script to brute force the answer was way more reliable than trying to do the arithmetic in its head, essentially. Once it stored that code snippet in its memory, it just kept pulling it out and using it. Problem solved, consistently.
That's such a great example of an LLM learning to use a tool effectively, recognizing that an algorithm beats manual calculation. And it's interesting, Claude 3.5 Sonnet didn't see the same jump on that task, right? It only went from like 12% to 14%. What does that tell us?
Yeah, that contrast is really informative. It highlights that DC acts like a scaffold, right? It provides the mechanism for learning and memory. But the actual success still depends heavily on the base model's ability to discover and encode those really good reusable strategies in the first place. In this case, Claude 3.5 Sonnet, even with DC, didn't seem to latch on to that general Python solver strategy. It kept trying variations of step-by-step arithmetic, which is just inherently less reliable for that puzzle. So DC can amplify good discoveries, but it doesn't necessarily create them out of nothing if the model doesn't find them.
That makes sense. It helps smart models leverage their smarts better by giving them a memory. Okay, what about the AIME math exams? These are notoriously difficult problems. Claude 3.5 Sonnet had some huge gains there.
Huge gains. Yeah, for Claude 3.5 Sonnet on AIME 2024, accuracy went from 23.3% up to 50.0% using DCQ. That's more than double. And on AIME 2025, it went from a really low baseline to 6.7% up to 36.7%, again with DCQ. And the analysis showed this was because it was successfully storing and reusing specific algebraic tricks and combinatorial approaches across different but related problems.
And GPT-4o also improved significantly on AIME.
It did. Not quite as dramatically as Sonnet on that specific benchmark configuration, but still very strong gains. 8% on AIME 2024 and 6.7% to 20% on AIME 2025 using the DCRS variant.
And it wasn't just these complex math problems. There was also the math equation balancer task. Simpler, but models still struggle. They went from around 45-50% accuracy to nearly perfect.
That's right, yeah. Both GPT-4 and Claude hit 98% to 100% accuracy there. And again, similar story to Game of 24. They figured out a reliable code-based way to do it, stored that approach in the DC memory, and just reused it, avoiding the usual errors you get with step-by-step reasoning on those.
Consistency through remembered algorithms. Okay, what about more knowledge-heavy tasks, like GPQA Diamond?
Right, GPQA Diamond tests deep knowledge. Claude 3.5 Sonnet got a nice boost there too, about 9.1%, climbing from 59.6% to 68.7% with DCRS. They noted that just adding dynamic retrieval helped push it partway to 63.6%, but the curation step in DCRS added that extra bit. Interestingly, GPT-4o only saw a very small bump on this one, 57.1% to 58.1%. The paper suggests that sometimes for GPT-4o on this diverse knowledge task, the retrieval might have actually pulled in confusing or slightly irrelevant info, which kind of underlines how important that curation or filtering step is.
Yeah, so the quality of what gets retrieved and curated is really critical. It's not just about having a memory, but a good one. What about the MMLU Pro Benchmarks in engineering and physics?
Claude 3.5 Sonnet showed pretty consistent gains there as well. Up to 8% improvement in physics, going from 74% to 82%. The idea here is that it was essentially building and maintaining these little reference guides in its memory key principles, common problem patterns for that domain. GPT-4o, again, showed slight decreases on these MMLU tasks with DC. The paper theorizes this might be due to the complexity of the domains, or maybe if the model's baseline understanding isn't strong enough, the retrieved tips from memory might not be applied correctly or might even confuse it. The model has to be capable enough to actually use the memory effectively.
Okay, so stepping back a bit, why does Dynamic Cheatsheet work so well, particularly in cases like Game of 24 or the math problems, and what are its real limitations?
Well, a big part of the success seems to be how it encourages better tool use, especially code generation. When faced with tasks that are computationally heavy or prone to arithmetic errors, like Game of 24 or equation balancing, models using DC seem much more likely to say, hey, I should write some code for this. GPT-4o, leaning almost entirely on Python for Game of 24 after discovering it, is the perfect example. Instead of grinding through calculations, it recognized a more robust algorithmic path, stored it, and reused it. So DC helps the LLM learn to think smarter, not harder, by using the right tools.
That's a really powerful mechanism, teaching it to delegate in a way. Identifying when an algorithm is better than just, thinking step by step. It's not just about what it remembers, but how it learns to approach problems.
Exactly. This leads to a really important comparison they make in the paper. DC's curated memory versus just naively appending the full conversation history, which they call FH. FH is basically just dumping everything that's happened into the prompt window for the next turn. No filtering, no summarizing, just everything.
Right, the brute force approach. And I imagine DC's active filtering and synthesis of just the useful bits makes a huge difference.
An enormous difference. The results are stark. On AIME 24, remember Claude Sonnet hit 50% with DCQ. With FH, it only reached 26.7%. And for GPT-4o on AIME 2024, it was even worse. FH actually dragged its performance down to 6.7% compared to the 40% it achieved with DCRS.
Wow. So just throwing the whole history in actually made GPT-4 perform worse than its baseline on that task. Why would that happen?
Well, think about it. FH can easily blow out the context window limit. But even before that, it dilutes the useful insights with tons of noise, making it harder for the model to find the signal. Retrieval gets less efficient, and it drastically increases the number of tokens you're processing, which costs more time and money. DC selective curation keeps the memory focused on high-value tips and code. It's uncluttered, easily accessible, and leads to much more reliable improvements. It really is quality over quantity for this kind of memory.
That makes total sense. Quality over quantity. But you mentioned earlier, it seems like DC doesn't work equally well for all models. Model scale and capability matter quite a bit.
Yes, the research definitely shows that. The effectiveness of DC seems pretty strongly linked to how good the base model is to begin with. The big guns, Claude 3.5 Sonnet and GPT-4o, saw major benefits. But their smaller siblings, like Claude 3.5 Haiku and GPT-4o Mini, showed much smaller gains, or sometimes even inconsistent results where performance didn't improve or slightly decreased.
So why do the smaller models struggle to take advantage of DC? What's holding them back?
Seems like two main things. First is just their core generative competence. For DC to build a useful memory, the model needs to generate correct solutions and good strategies often enough to populate that memory with high-quality stuff. If the base model isn't very accurate to start with, the memory just fills up with noise or stays empty. The positive feedback loop never gets going.
Right. Garbage in, garbage out for the memory. And the second reason.
The second is limitations in contextual understanding and memory curation itself. Smaller models often aren't as good at understanding long contexts or generating well-structured, comprehensive updates for the memory. They might not retrieve the best examples, or they might misinterpret or misapply the strategies they do retrieve. So basically, DC amplifies the strengths of capable models, but it can't magically fix fundamental reasoning weaknesses if the base model just isn't up to the task.
That's a really crucial takeaway for anyone implementing this. It's a booster, not a replacement for core model capability. So besides model scale, what other limitations or challenges did the paper point out for Dynamic Cheatsheet?
Well, one challenge is potential retrieval bottlenecks and noise. If the system pulls back a past example that isn't actually very relevant or is maybe even misleading for the current query, it can obviously cause confusion. We saw hints of that with GPT-4o on GPQ-8 Diamond sometimes. Getting retrieval right, especially across diverse tasks, is hard.
Yeah, bad recall can be worse than no recall. What else?
Faulty heuristics. If the model makes a mistake but incorrectly assesses its solution as good, that flawed strategy can get written into the memory. Then it gets reinforced and reused, leading to repeated errors. So maintaining a clean and accurate memory is vital, and the self-assessment isn't perfect. There's also a point about long context generation versus understanding. Models are generally better at reading and understanding long prompts than they are at generating equally long, coherent, well-organized text for, say, a memory update. Sometimes they might generate abbreviated or incomplete updates, which could degrade the quality of the stored knowledge over time. This might suggest a need for more structured external memory stores in the future, not just free text.
That definitely opens up some interesting engineering avenues for making this even more robust. Okay, so wrapping up, this paper really offers a practical, powerful way to give LLMs that missing piece, the ability to learn from immediate experience without needing full retraining.
Exactly. Dynamic Cheat Sheet kind of bridges that gap between the totally isolated way LLMs usually process queries and how humans learn cumulatively. It's a concrete method for these black box models to get better over time, fix recurring mistakes, all within the inference loop without parameter changes. It feels like a significant step towards more genuinely adaptive AI.
And it clearly brings efficiency gains too, right? Less reinventing the wheel must save a lot of computational effort.
Absolutely. Once a model finds a good strategy, like that Python script for Game of 24, DC lets it reuse that knowledge instantly. It doesn't have to spend tokens and time rederiving it every single time. There's an upfront cost to discover and curate the good stuff, sure, but that cost gets paid back many times over in subsequent queries. It's a net win for efficiency and performance in the long run.
Looking ahead, the paper noted DC works particularly well when test examples have similar structures. That hints at something like curriculum learning, maybe?
That's a really cool possibility, yeah. It suggests you could potentially feed the model simpler problems first to let it build up a solid base of heuristics in its dynamic cheat sheet. Then, that memory could bootstrap its performance when it tackles more complex problems that share underlying patterns, like teaching math basics before calculus.
And they even floated the idea of maybe having different specialized memories, like a combinatorics cheat sheet, a physics cheat sheet.
Right, hierarchical or modular memory. That opens up a lot of possibilities. Which brings us to maybe the big closing thought here. As LLMs keep getting bigger and more capable, how might frameworks like Dynamic Cheat Sheet change how we even think about knowledge and learning in AI? Are we moving beyond just static knowledge baked in during training towards systems that are truly adaptive, learning continuously from their ongoing experience? It's a fundamental question about the future nature of AI intelligence.
A great question indeed. Something for you, our listeners, to think about as you follow the rapid progress in this field. Thanks for joining us for this deep dive into Dynamic Cheat Sheet.